Now we have a well here. And so notice that again now our energy is above everything. And the first question relating to this well on the worksheet is how the boundary conditions at the left and right edges of the well compared to what we had before. So, that's a bad place to, let me pause it here. Again, now we have sinusoidal terms, two of them on the inside, two sinusoidal terms on the left and one on the right. If we look at the sum, we see that the wave function is continuous and its first derivative is continuous. So even though it might look like there's a discontinuity here, really you have to add these two on the inside, and then at the left edge, the sum of those will equal the sum of these. So again, that sum is the same. So the boundary conditions are exactly the same. The wave function and the first derivative have to be the same. Now, let's drag the well slowly to the right a little bit, and let's watch how the transmission probability changes. So right now, the transmission probability is 0.99, and as I drag it to the right a little bit, it's going down, but then it went back up. So again, here, it's like 0.95. Now, notice here what's happening. Here, when I look at the sum, right? So keep in mind that this is the probability density. So if we're looking at the probability density, we kind of see that it oscillates and there's, it goes from a bottom position to a top position. If we look at what's happening on the inside, again, a little bit difficult to see, we see that, okay, it oscillates up and down and then back down. So this is like, kind of not a nice number of oscillations there. And so that gives us our minimum transmission. When we get to maximum transmission, this is again a situation where it goes up, down, up, down. Okay, if you look, it really is fitting nicely. So when you have that integer number of half wavelengths here, that's where you get that 100% transmission probability. And here, okay, it's telling me transmission is 1. We see a little bit of a reflected wave, but there's going to be some point where it's basically 0. The simulation doesn't have perfect accuracy. Pretty good. So again, you have that integer number of half wavelengths here. So that's the key. And again, as we drag it to the right, it goes down again, and then it goes back up and down and back up and down and back up and down and back up. And that's really just oscillating with adding another half wavelength every time. So now let's switch back to a barrier. So I'm going to reset all. Yes, reset all. And now, if you notice, I have a wave packet. So now the question is to try to understand what happens for a wave packet that tunnels through the barrier. Now, I'm going to drag this down just so that I can actually have a kind of more of a barrier to work with. So the first thing to remember about your wave packet is that it's a superposition of many different momentum states. So that's the same thing as saying it's the superposition of a lot of different energies. So we see at the beginning a Gaussian wave packet, and it's traveling to the right. Now here I can control that initial position, I can control my width. So as I make my position better defined, that means I have more and more energy components. So what we've learned already about wave packets is that once it starts traveling, it is going to spread out. So even before it's interacted with the barrier, it's spreading out. Now then, it starts interacting with the barrier. Now notice here, it looks here like it's sinusoidal. Okay. But now, okay, sinusoidal, sinusoidal, and then we eventually see weird stuff happening here. What on earth is happening here? Now there's basically interference. We can think of this as some wave being reflected. Now notice that we no longer have the control of looking at the sum and the individual components because this already is a bunch of sums. And so eventually what happens is we have our big spread out wave packet over here, and we have some nonsense happening on the right. So let's restart this, and now let's make it just a little bit wider in space. What that means is our momentum distribution is more narrow. I let it play forwards. Again, it's spreading out. We see those oscillations as it goes through. Some weird stuff happens. Some of it reflects. And so you can kind of see, even here, it looks like there's one wave packet here and one wave packet there. Now what happens let's move this down here. Now notice that some of our energy is still above the barrier, but most of it's below. So what happens? We see it come up, we see it come up. Now notice, again, there's kind of a sinusoidal behavior here. Some of it gets through, but then we see this messy interference here, and then most of it is being reflected back. So again, we had a little bit of that wave packet transmit through, most of it's reflected back. Now, one of the things that's a little bit difficult to do is to actually try to look at what the wavelength is. Let's see if we can try to figure this out. Now remember that because this is going to be the superposition of many different things, there's not a fixed wavelength, but on this side it looks like it's about one box, a little more than a box separate. And when we look over here, we see that, okay, it maybe is a little bit longer, right? A little bit difficult to see. However, if this has a shorter wavelength than that side does, which I think is the case, that's effectively saying that we have transmitted more of our higher energy components and more of our lower energy components have been reflected, which is what I would expect. So let's make this a little wider and see what happens. So again, we're going to go through, and now you see, oh, it's not much is making it, right? So again, we kind of have this decay. Again, there's some of a sinusoidal here because some of that energy is above. Oh, it's trying to decay, and you can see a little bit of that sinusoidal. Okay, and a little bit made it, right? So again, we see that some component has made it. And okay, so now if we try to zoom in again, it's a little bit difficult to see, but again, more than a box in between them. More than a box, and over here pretty close to one box between them, right? Again, it's not going to be perfectly sinusoidal, so what I'm doing is kind of hand wavy, but again, the amplitude is lower here because mostly it's being reflected, but the higher energy component is primarily what's being transmitted. So we can reset all again, and so the notion being that when it hits this, some gets transmitted, some gets reflected, but now we've seen that different energies have different reflection and transmission probabilities, and since our wave packet's made up of those different energies, we see this weird behavior. Now, what if for funsies we make this a well? What's going to happen? Well, again, some of it gets transmitted, some of it gets reflected, but now more of it's getting transmitted, but now we've seen that the transmission probability is going to depend a little bit on what the energy is based on whether you have those integer half wavelengths inside the well or not. So again, there's going to be an energy dependence, so you don't get, a nice, beautiful wave function, the same sort of Gaussian packet. We get close to that transmitted, but something gets reflected and it's not going to be affecting all of our energies equally.